Hello, my name is Yanni Adoni, and I am an emeritus professor at Turner University, and that's what brings this presentation together. I'm also fellow of the American Welding Society, so I'm wearing my uh, medal. Just to clarify, my co-authors, Mr. Work and Paula Vadvoy, also worked at Turner University at one time. That's why that brings this together. But right now, Robert works metallurgy and applied mechanics in Chicago, Illinois, and Vodboy Balázs is the currently department head of the material science program at the Budapest University of Technology and Economics. With all that introduction, what is this talk all about? It's about bond lines, bond line characterization, high frequency welding, and this is what brings us together, Turner University, Longview, Texas, where we worked together years ago. By the way, I'm currently senior professor at University West in Sweden. With all that out of the way, let me try to characterize a little bit what high frequency resistance welding, we also call it ERW, or electric resistance welding. It's been around for a long time. Some of you might be familiar with, some of you might not. Basically, it's a solid state welding, a form of forge welding, where induction or contact electric resistance is basically accomplished by skin and proximity effects, which we'll talk about later. And it's a mostly continuous process, fully automated. It works really fast in longitudinal seams in tubular products. And here is a schematic of how it looks like. Scalps are cut and then folded together and then fed through what we call welding rolls. And then in this case, you see an induction coil heating up. And I will refer to this particular area here. I highlight right now a V. Looks like the letter V, from where the final product comes out on the other side. You can see here to the right an application in which contact high frequency current is passing on to this particular heated edges, which are squeezed together, and the product comes out on the other side. So you can basically split the high frequency welding in several stages. At the beginning, where the contact starts heating up the edges, these are the contacts represented schematically. When the edges begin to heat, well, obviously this happens very fast. When they start glowing, which means that they reach a temperature over 1,000 degrees centigrade, we bring them really close to one another. And yes, this is a solid state process, yet the edges begin to melt. So it's really hot when they are squeezed together. Important is that the metal, the melted and resolidified material is squeezed out from the interface, and you end up with a joint. And basically, the topic of my talk is the bond line, which is a metallurgical feature you will see in any cross-section along the middle line of the weld. At the end, by the way, the excess material is shaved off. We call that scarfing. And this can happen very fast. Small tube welding can go practically at sometimes hundreds of feet per minute, but then oil country tubular 10-inch diameter steel at maybe half-inch wall thickness can weld at 70 feet per minute. In any case, this happens very fast. And that's really produces millions of miles of weld since they invented it. Theoretically, when you look at the energy distribution, you see to the right that heat is generated by high frequency, and I mean 300 to 900 kilohertz, or tens of thousands of hertz, hundreds of thousands of hertz, up to 1 gigahertz frequency, which forces the heat to occur at the surface because of skin effect, and then the energy is released on the other side where it dissipated. So we have a thermal and mechanical effect to the right, and then the thermal effect when the heat is dissipated to the left, kind of giving you an idea how this process works. So what is the bond line? the topic of this subject is this particular little line in the middle, which is highlighted by this arrow, which has different characteristics than the rest of the weld. Many times people suspect that that bond line is a source of failure, and that's why I wanted to have this conversation to give you some idea, because when people sometimes measure the hardness in that region, they find it excessively high, like in this case. Yet sometimes if you weld a different grade, like a 1018, it is much lower. So it has a weird behavior, this particular bond line, and also, if you notice, it doesn't follow the hourglass shape of the what we call thermomechanically processed zone, a TMPZ, highlighted there. So the bond lines are always straight, no matter what kind of material, what kind of total TMPZ looks like. Here's an example of an austenitic stainless steel 304L. Made, you can see 210 kilohertz, 58 kilowatts. We talk about very high powers. But you'll see what this is. The bond line is only 37.1 microns wide, and I will be talking about the width of this bond line several times, but they never really exceed 60, 80 microns. Only in abnormal cases it's wider than that. Yet it will always remain parallel edges, and it will be always in the middle. So please take a note of that. Now we looked at service failures to try to see what is the panic about these bond lines. People keep reporting that they are afraid of them. So we reviewed the paper by a very extensive report by FABTECH, which reviewed 286 welded pipe failures, and we're talking about 60 years span. What they found that there was a really big mix of resistance butt welds, even back to the years when they used DC current or low frequency current to heat up the edges. So basically these these pipes either blew up in hydro testing or in service, and about half of them were caused by cold welds. In other words, the edges were not squeezed together properly, there was no bonding, there was an oxide layer in. We talk about a flaw. We call them lack of fusion. There's seam corrosion when, again, the edges did not bond properly and corrosion occurred along the center line. And then there were so-called hook cracks, which were about a quarter of these. They were lines of non-metallic inclusions from steel production, which actually came apart. That's basically the three types of defects they found. Yet they have never found any weld of good quality with good bond line that actually failed. So that's an indication that that good bond lines never fail, as we observed also. And this is basically an overview of those bond lines. So what we did was a work at La Trinity University in which we experimentally combined a thermomechanical simulator called a Glebel with a Thermotool welder, where I want to acknowledge the help and the support from Thermotool Corporation. We also gave us the opportunity to look at hundreds of production welds made on lines that have Thermotool high-frequency welders. And so this is a close-up of a bond line. You can see 3394, so it's the same low order magnitude of bond line of ferrite in an austenitic steel. So here is the experimental setup. You can see here a modified Glebel 1500 with a 100 kVA high-frequency welder, and basically the Glebel provided the mechanical cycle to push the two edges together, while the high-frequency welder, which came in perpendicular to it, provided the heating. And this really was a very difficult undertaking, but we wanted to replace the resistive heating of the Glebel with this inductive heating coming from a really high-power high-frequency welder. And you can see we had a multitude of thermal cameras looking at this. We measured not only temperatures but deformations and rates and things that came with the. So it was a highly controlled experimental setup. We used solid bars. Then we used pairs of bars, and we basically welded them together to reproduce high-frequency welds in a highly controlled condition in order to separate the thermal from the mechanical effects. That was the purpose of this work. This was funded by the American Iron, Steel and Institute. Later on, U.S. Steel and Thermotool participated in funding. Again, we were aiming at separating thermal from mechanical effects. And again, solid bars, you can see here, we also looked at welded sheet. We modified this for dual phase 600. You can see two sheets brought together and welded along that line. And here's an example. Maybe excessive flash, which we haven't reviewed, but it was good quality weld nevertheless. So what we found that mostly what really varied was the width of the thermomechanically processed zone. This is actually a simulated weld. This is not an actual weld, although it looks very similar to an actual weld. And here is you can see that we looked at the thermal inputs where the power, frequency, and the gap between the material, and then mechanically was offset rate, and the outputs were cooling rates, temperature gradients, and total loading time. Important to notice again that this bond line doesn't seem to change no matter what we did with the thermomechanically processed zone. So again and again the same topic comes up. The bond line does not change much, 2734 microns. Here's the example how the thermomechanical process zone width varied with frequency. As the frequency increased, you can see the thermomechanical process zone width also decreased with increased frequency, but the bond line did not change much. So we started looking at really, again, the fact that the TMPZ width did decrease with frequency, so it was a thermal effect, we concluded, but the bond line was not much deterred, and therefore we started concentrating on more of a squeeze out that is a mechanical effect. So we started focusing on the fact that the bond line is a remnant of the mechanical cycle more than of the thermal cycle because it did not change much. So we came up with several theories. Here is one, the cooling rate effect. So the heat input changed in such a way that we had high heat input, low heat input. Well, for the same frequency, we found that a high heat input, we had a wider TMPC zone, and low heat input, we had a narrower one. So when we squeezed them together, the resultant product was wider at high heat input and narrower at low heat input. Yet the bond line width did not change much. The same happened when the frequency changed. In this case, it was not the cooling rate, but the thermal gradient, that is how steep the gradient was. At low frequency made it very wide, at high frequency made it very narrow. So that basically said after welding it was a similar behavior, and we ended up again with bond lines which varied very little within this group of experiments. So we concluded basically that for a perfect weld we would simultaneously require low heat input, which means in practice fast welding speed, that is high cooling rates. Imagine the pipe coming really fast. That's the only way you can accomplish low heat input. We also concluded that we also have to use very high frequency, or the highest possible frequency, to make the gradient narrow and accomplish as much squeeze out as possible. But at the same time, the total offset had to be high to squeeze out a lot, and very surprisingly, the rate at which this provided the best grain size and push out was a low offset rate. And here's a little bit of a contradiction. So if you travel really fast, your offset rates will be high, yet you really need low offset rates not to work hard in the material. So finding the balance between those really makes a weld, perfect weld accomplishable with low probability. Like in a perfect weld, the bond line width would be 0. But again, unfortunately, number 4 condition is opposite to number 1, that you'd like to weld really fast, but due to deformation slowly. So that's why you see variations within systems and powers and all that, because all this has to be simultaneously very, very hard to accomplish. So that was really basically what we concluded. Yet again, back to the bond line. What matters really is how they shaped and how uniform they are, how are they oriented relative to the wall thickness, and how sound they are. And really, that's really what remains important about bond lines. For instance, if you look at the lack of parallelism of an insufficient ID squeeze out, here's an example of a TWIP steel from the literature, 800 megapascal strength, welded at 110 kilohertz, which is low in my opinion. And look at what happened. They clearly showed inclusions at in an unetched sample at the ID side of the pipe. And notice what happens. Right there, the parallelity changes. So the material becomes trapezoidal, which means that it did not squeeze out properly. So the fact that this bond line is wide, that's only one thing. In my opinion, it's too wide. But again, they did not squeeze out properly at the ID, and they have lines of inclusions. As a consequence, when they did a flare test, they actually opened those inclusions up, and lo and behold, they were lack of bonds. It's very little bonding. It was oxide inclusions at the interface. So the bond line parallelism is really important. At the same time, its orientation is important. For instance, if the bond line is not perpendicular to the or radial as if it were, but is skewed like this, or in this case, it's clearly there was a poor edge presentation, and that also causes not only thinning of the wall. Notice that after shaving off the excess material, this part of the weld is much thinner than the other side, so that's not good. The pipe could explode, and it also produces a notch. So again, if the bond line is not perpendicular to the surface or it's radial, that's also a problem with overscarping. I just mentioned that. So in these past 15 years, instead of concentrating on the shape orientation and the size of the bond line, people came up with lots of theories. And one myth is that the bond line, which has low carbon, low hardness, which found there is a decarburized layer. In other words, the edges must have decarburized, and therefore they were retained as a decarb layer in a final weld. However, clearly, the bond line is never decarburized, but it is actually just delta ferrite, which was retained at high temperature product during X-ray diffraction. We clearly showed that it was only delta ferrite together with martensite and bainite in higher carbon grades. Here's a proof. We did a lot of X-ray diffraction analysis, but nevertheless, there is no proof that there is a decarburized line. It is simply delta ferrite. A recent paper which came out last year, well, actually this year, from Ridrum Lee and University of Alberta, confirms that they use physical simulations to show that when you squeeze out two edges together, even by DC welding, you will produce austenite molten product, austenite and ferrite, and delta ferrite will be retained at the bond line. So this is not only my conclusion, but it is Dr. Lee's conclusion as well from University of Alberta. He came to this conclusion totally independent of me. We also notice many times that in high alloy grades like 4130s tubular, where we have increased in hardness from the base metal almost 3 times in the ERW weld, the center line, which is probably retained delta ferrite, has lower hardness right there. So that's not a decarburized layer, that's simply delta ferrite, period. The other myth is that the bond line is a flaw and it has to be limited in width or eliminated or whatever. But in reality, sound bond lines are just thermomechanical process areas which were not squeezed out. And so they're not flaws. They're basically, you can reproduce these by reheating solid bars. And here is a solid bar reheated. This happens to be duplex stainless steel, reheated in the Glebel and pressed together with low strain rates and high total offset, and we could reproduce perfectly well bond lines without having two pieces together, showing that this is not a flaw. It is just a metallurgical heterogeneity because of the steep thermal cycle and mechanical cycle it experienced. And the final myth that I wanted to bring to your attention is that because it's sometimes high hardness in alloy steel is found there, people concluded that bond lines are dangerous because it can have low toughness. Well, in reality, the entire weld has poor toughness at this stage. For instance, if the bond line is 20 to 6 microns wide, where are you going to put the notch? Because brittle failures can initiate anywhere, not necessarily at the bond line. And here's an example. The typical notch of a Sharpie specimen is 0.25 millimeters, way bigger than the bond line. And then what happens if somebody doesn't place the notch right there or here, the result should be the same. And people recognize that. The recent API spec shows that if they want to establish the toughness of a ERW weld, they should place the notch somewhere around the bond line, 0.25 to the left or right. Regardless, they recognize that the so-called fusion line is really not that important. So, if somebody is really bothered by these bond lines, they can erase them, because post-weld heat treatment basically the so-called inline seam anneal can dissolve all these constituents. And so you end up, for instance, in this case, 304L austenitic stainless steel, reheated and then air-cooled. You can see that before, as welded, you have that ferrite bond line, post-weld heat treated, completely disappeared, showing that it's neither decarb, nor inclusions. It is just a different microstructure that actually you end up paying some price by having grain coarsening in this case and probably lower toughness, but this was austenitic stainless steel. I don't think toughness was a concern. So it can be costly to do this kind of post-weld heat treatment in line. You can see here the welded pipe has to run under an induction coil. You have to make sure that the weld is not squeezed or skewed from the induction coil. There are certain complications with this. But if you're bothered by bond line, by golly, erase them. That's my point. So, in conclusion, we concluded that bond lines are the result of non-equilibrium thermomechanical processing and can be erased. And their width is a function of mechanical deformation and temperature, really, and they are indirectly related to the weld width, so we shouldn't be concerned that much about bond line width. The bond line shape, orientation, and uniformity, on the other hand, are important, and we can use them to indicate defect formation elsewhere along the seam, but the bond lines never failed. And this is the main message of my talk. And after many, many years of being involved with the subject, I've never seen a bond line fail. And therefore, I would challenge anyone listening to this talk to call me in case they have a disagreement with me, and show me. I can assure them that if bond line failed elsewhere in the weld because they had the flaw, I wouldn't argue with that. But sound bond lines do not fail, and we shouldn't be so concerned about them. We know what they are. We have to look at their shape, orientation, and uniformity, period. Thank you for your attention. Bye.